Good morning. My name is Prasun, Dewan, and I get to present this paper. And I'll introduce my co-authors when I talk about the topics on which they worked. Let me start by explaining the various terms in this title. By concurrency, I mean thread creation and implementation, synchronization to provide mutual exclusion, and coordination to manage thread interdependencies. Automatic testing means using a testing framework that provides information about how well a program meets its requirements. This information can be provided to the author of the program or another interested party, such as a manager or, in our case, an instructor. Now, automation does not imply complete automation. If you've used the GradeScoop GUI, you know that all checking must be done manually. And what GradeScoop does is automate the time-consuming task of navigation and rubric management. So I call such a system a grading management system. Such a system, of course, is of no use to the author of the program. It's of use mainly to an instructor who's scoring a series of assignments. If you want complete automation, you have to write custom tests, which can be found and invoked automatically by an infrastructure. And you see here the outline of such a test. It calls entry procedures in the tested program, providing it with input, and then checks if the expected output conforms to the actual output. And for this to work, the author of the program must provide entry procedures with the signatures that are expected. Okay, so we not only have problem requirements, but also testing requirements for the program. To illustrate, let's take the example of a program that sums up a bunch of values. If the tester expects a procedure called add that takes an array as an argument, then we cannot write a solution that calls the procedure sum and expects a vector as an argument. So these testing requirements are peculiar to testing frameworks, and they are not part of a grading management system. And depending on the situation, you may want to use a grading management system, an automatic tester, or perhaps both. I've talked about these two terms, concurrency and automating testing, independently. Unfortunately, they don't go together today. And this add example shows why. Whether add is implemented serially or concurrently, the output will be the same. So you cannot use a testing program to validate the concurrency requirements of this solution. So as a result, we restrict ourselves to those concurrent problems that visualize concurrency in the user interface. And you see here an example. This is a simulation of a boy bouncing a ball. Both the ball and the boy are separate threads. And if in the simulation the boy moves with the ball, then we know that the program has been correctly implemented. Here's another graphical simulation, this time of two trains that are currently on the same track. Each train is a separate thread. And if one train switches tracks to avoid colliding with another train, again, we know there is correctness. Here I can actually play a video. So in this example, each character is a separate thread. And the fact that they're moving in unison means that the concurrency requirements have been met. So we are restricting ourselves to visual concurrency, but a problem is that current testing frameworks are not designed for visual graphical user interfaces. Okay. So let's take the example of a grading management system first. Current systems are passive. They don't have the ability to run the programs they store. As a result, we can't view the user interface. Now, you can use an external tool such as SSH, but then A, you don't get graphical user interfaces directly, and B, you don't get the benefits of grading management, rubric management, and navigation. Okay. So we created a solution of a non-server-based grading management system that provides a command to run the current student's program which could create a textual or a graphical user interface. It provides commands to go to the next student or the previous student. And it also provides a rubric that can be filled with a few clicks to score the program. Okay. And this system is independent of the programming language, and you can imagine it was a lot of work. But if you want automatic testing, you would like to be able to write tests that make the same inferences that humans would make to establish correctness. That creates another problem. How to programmatically provide input to the tested program and how to programmatically get the output when the user interface is graphical. There has been some work in testing graphical user interfaces, but unfortunately the solutions are all non-standard and they don't work, for instance, for popular Java toolkits with which I am familiar. So our solution relies on an abstraction that's above the UI toolkit. This is the mother of all design patterns, and it's actually implemented by all the GUI frameworks known to us. It involves creating all visualizable state as model objects. They don't actually visualize the state. That is visualized by view objects. And a view is connected to a model by calling an observer or registration method in the model. So now the view becomes the model's observer, and the model becomes an observable. This means whenever a write method is invoked on the model, a notification method is called in the observer to tell it what changed in the model. Now, any object that registers itself with the model can become its observer. It doesn't have to be a view. So our solution has the testers become observers of all the observable models and provide input to these models and then trap the output state changes through notification methods. Okay. So now in this picture, our custom tests now have notification methods and they can do anything they feel they want to. And we also have code that initiates, registers the test with the tested program, calling an entry point in the tested program. In this case, it's called register. And then provides input to the models. And then what it does after that is up to it. And it depends on what was done in the notification method. This registration call is made in the testing thread, and the notification method is called by each thread in the tested program that changes an observable model. So our custom program tests now become themselves potentially complex multi-threaded programs, and there's no guidance as to what these ... should do. I call this a direct approach, observer approach, because a custom test is directly an observer of the models. To solve this problem of no architecture and multi-threading, we provide a more indirect approach where the notification method is now part of the infrastructure. And it is this infrastructure that executes the different threads that invoke the notification method. Now, the application programmer is involved in writing only a testing thread, which registers not itself with the models, but an infrastructure observer. Then it provides input. And the infrastructure stores the events that are received by it. And these events can be then received, can be waited for and then received by calling this wait for notification method, which returns when some application specific condition is met by the events. And at this point, the testing program can check the events for what is expected. And to make that check procedure easy, we provide some generic operations to query the stored events in the events stored by the notification method. Okay. So because of these queries and this database, we call this infrastructure a DBMS of not arbitrary data, but concurrent notifications. Okay. And our implementation is Java-based, and it's based on the Java Observable Bean API, which is the standard. Okay, so I've talked about two components of our work, an active grading management system and concurrent notification DBMS. This summer, we taught an object-oriented course, and the concurrency assignment was graded manually using the active grading management system. We also used a direct observer approach to implement the concurrency test for this assignment. This was before the DBMS was created. In fact, the DBMS was created in response to the problems we faced in writing these tests. And once we had the DBMS, we used it to write tests for several versions of the dining philosopher problem, including a sequential. We also redid the test for a concurrency assignment using the DBMS so that we could compare the two efforts. To get more data, we also looked at the student experience with our tests. Andrew wrote code to track how many students ran tests on their computers. And Andrew and Ken also tracked how many attempts were made on a test before it reached its final score and how much time these attempts took. All the data gathered by these log tests were visualized by Sam. And our tests were meant to identify problems with students' code, but they themselves can create misunderstandings about their requirements and their output. So to figure out what kind of problems the tests themselves created, Bowen and Howe looked at all Piazza posts and recordings of Zoom sessions of office hour visits. So here are our findings. First, as far as we know, nobody has ever written a test program for a dining philosopher solution. We were able to write tests for all of our versions using the abstraction of the DBMS. And more interesting, once we had written the sequential test, adding the concurrent test required very little new code. As you would have expected, the DBMS made writing of tests much easier. At least the test was smaller. And all students ran tests locally on their computer, even though they could use the Gradescope server to run these tests. Sam's visualization made it easy for us to spot students who had atypical test attempts and test time. And yes, students had problems with the tests, but we solved them as they arose. And the number of these problems was smaller than the number of problems with concurrency itself. We used both manual grading and automatic grading. Manual grading was done after automatic grading to validate the results of automatic grading. So it went very quick and took very little time. So our conclusions are that passive grading management systems and infrastructures to call tests do not test concurrency. And our solution involves creating an active grading management system and a concurrent notification DBMS, which we found makes grading more efficient by instructors. Perhaps more important, tests were used by students to meet assignment requirements. And even more important, tests provide awareness of student progress and homework assignments, and in future could potentially identify students who need help. We also need future work on how to expand the range of concurrent assignments that we can test automatically. And if you're interested in to do any of this work, please send me a mail, and thank you very much.